Okay, everybody, we're going to talk about the greenhouse effect and cover 9.3 and 9.4 in this video. The first one is discussing exactly what the greenhouse effect is. We're going to identify principal greenhouse gases such as methane, carbon dioxide, nitrous oxide, and chlorofluorocarbons. Discuss why water vapor isn't such a big deal in this instance, how it influences temperatures on Earth, and discuss something called global warming potential. So first things first, the sunlight coming to Earth, some of it gets reflected back into space, some of it gets absorbed by clouds and gets radiated back into space or back down to Earth, and some of it strikes Earth. And once it strikes Earth, depending on the type of surface that it reaches, it will either be reflected back into space because it will have a high albedo, means a high reflective potential, or darker low albedo surfaces will absorb it and convert it into infrared radiation or heat, or somewhere in between, depending on its relationship to light or dark, how well it absorbs light. Now, the problem, well, the greenhouse effect isn't really a terrible thing. Gases in the atmosphere trap heat from the sun and radiate it back down towards Earth. So when infrared radiation or even light sometimes is reflected back into space, um, this can be absorbed by these greenhouse gases and then sent out in any direction, but many times back towards Earth. But without this greenhouse effect, life wouldn't be around. We wouldn't be able to survive. Life would just be too cold. So, solar radiation, light waves like UV and visible light strike the Earth's surface. When heating, Earth's surface releases infrared radiation. Greenhouse gases absorb infrared radiation, radiated both out into space and back towards Earth. The portion coming back to Earth is the greenhouse effect. Now, what are our sources? The most important greenhouse gases, we have these four here: carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, hydrochlorofluorocarbons, and hydrofluorocarbons. So we know fossil fuel combustion, decombustion, deforestation for carbon dioxide, natural gas extraction and combustion for methane, animal culture, agriculture, anaerobic decomposition, and melting permafrost, methane, nitric oxide, agricultural soils, which is the denitrification of nitrate, especially in overwatered or over fertilized soils, and our chlorofluorocarbons and their friends, refrigerants, and blowing agents and aerosol products. Water vapor is also a greenhouse gas, as it turns out, but it spends so little time in our atmosphere that it doesn't really drive too much temperature change. Now, the problem, of course, is that we have too many of these gases at this time, so we're seeing our planet heat up quite a bit. So, how do we measure this in a real scientific way? Well, we have something we can measure how much a given molecule of gas can contribute to the warming of the atmosphere over a 100-year period. That's global warming potential. And this is based on residence time, how long it stays in our atmosphere, and how well the gas absorbs and radiates infrared radiation, which is known as infrared absorption. And so our standard is carbon dioxide. That is a GWP of 1, right? All other gases are compared to carbon dioxide. Now, carbon dioxide is very abundant, but in terms of its capacity for staying in the atmosphere and absorbing heat, it's much lower than the others. So, methane has a global warming potential of 23 to 84, remains in the atmosphere for around 12 years and absorbs more infrared than carbon dioxide. Nitric oxides, about 300 compared to our 1 for carbon dioxide, remains for about 115 years and absorbs much more infrared radiation than carbon dioxide. And then our chlorofluorocarbons are just wild. 1,600 to 1,300 compared to 1. Remain for 50 to 500 years and absorb much, much, much more infrared than carbon dioxide. So actually, yes, this is a really, really potent greenhouse gas. Um, so you should be expected to explain how the greenhouse gases in the atmosphere contribute to the heating of the Earth's climate. You should be able to identify a greenhouse gas that has a global warming potential greater than 1, its sources as well, and why it has a GWP greater than 1. And you would discuss residence time or infrared absorption. But now we're going to talk a little bit about the increase in greenhouse gases and how bad that can be. So we're going to talk about really threats to human health and the environment posed by these greenhouse gases, and several problems throughout. So we're going to start with sea level rising. Now, most people believe sea level rising is because of the melting ice caps and such like that. But another huge thing that we don't often talk about is thermal expansion. As water molecules get hotter, they actually expand. Hot things expand, cold things contract, and that's true of water. And then until it turns to ice, and it does the opposite. But as a liquid, it expands when it heats up. And so thermal expansion is a serious part of sea level rising. There's a lot of water there, and even just a slight separation between water molecules, a slight increase in that separation will cause an entire ocean to rise. And then the one that you're probably most familiar with, the melting of the polar ice caps. This water flows into the oceans and leads to sea level rise. Increased greenhouse gases lead to warmer climates and more melting of ice sheets at the poles and the glaciers. Now, why is this all bad? Well, look at this. Actually, this is interesting. From 2005 to 2020, this is thermal expansion and added water, mostly meltwater. When you combine these effects, global sea level rise, we can see here we are. From satellite, we can tell that this is for certain happening, and we can project exactly how much the sea level seas will rise. Now, flooding of ecosystems is a big one. Estuaries like mangroves and saltwater marshes, some of the most productive ecosystems on the planet, are not going to be able to adapt necessarily. And Arctic species and tundra ecosystems, polar bears, penguins, reindeer, they depend on sea ice and other specific conditions. These are specialists. So as the ecosystem change, they won't be faring so well. And the loss of thaw freeze cycles that glaciers go through, because these glaciers are sitting on top of water, and as the sea levels rise, this is going to affect their formation. And many people actually depend on this glacial melt for drinking water. Now, the big one is relocation of human populations. Most people live on or near the coast or some source of water, like a river or a lake or something like that. But increased flood frequency, higher insurance and repair costs, loss of property, saltwater intrusion is going to be a real serious issue. And we're going to see refugees being forced from the coast inland, and we're going to need to prepare for that. And the better we do that, the better we'll feel. Yeah, better things will be. Disease factors, of course, are something we have talked about because their range is going to be expanded. Because of the greenhouse effect, we're going to see quite a bit of warmer temperatures in the northern and southern parts of our world. And so these disease vectors, these mosquitoes, will be able to survive there for longer periods of time and be able to spread disease for longer periods of time. So we'll need to prepare for new diseases in places that hadn't had them before. The best example is the Aedes aegypti mosquito. You won't need to necessarily remember its specific name, but mosquito range, this is the one that spreads dengue fever, Zika virus, and yellow fever. It exists 12 months out of the year in these places currently. And then up here, it doesn't exist at all. And so we can see how it's ranged. 12 months changes like 5 months, 4, 3, 2, 1, and then you won't find it. But year 2080, that's expected to change. And so this is an entire population of people that will be expected to prepare for diseases or vectors specifically that they had never seen before. And so, yeah, it can be quite startling. So you might be asked to identify a region where malaria rates may increase in 2050 and explain how climate change may contribute to an increase in malaria in this region. Disease vectors are going to be um, the one that you focus on because you're going to see, I'm sorry, these are both 2080, I apologize, but you're going to be expected to describe how temperatures are expected to be warmer for longer in periods in more northern latitudes and more southern latitudes as well, therefore allowing the spread of something like Zika and yellow fever and dengue fever.